Hey guys, I'm back with your favorite, a physics video. So this week we can finally begin teaching you guys more. So what I've done is I've made a quick slideshow that goes over the highlights from the EdGenuity lessons. And anything that I'm not covering here is going to be stuff that's not on the quiz. So I have covered the highlights, the stuff that we believe is the most important. Everything here is in EdGenuity. So I highly recommend working in EdGenuity to get more practice with it. It wasn't intended to be the end all be all where you're going to get everything you need, all the practice, all the examples you need. So you're going to want to continue working in EdGenuity for that stuff. But I do get to finally just explain things to you in a way that I would myself, and since we made the quiz, it'll be worded in ways that should be familiar to you. So let's go ahead and get started with the properties of sound waves. So this was the first EdGenuity lesson that you guys needed to go over. And a really important property of a sound wave that it was talking to you about was intensity. So intensity of a sound wave is the amount of energy that's flowing through an area over time. So remember, waves carry energy. That's their whole thing. So intensity is the amount of energy that's going through an area. And this intensity is actually measured in decibels, which is a measurement you're probably familiar with. When people talk about sound, they talk about it in decibels. So they're talking about the intensity of that sound. And that intensity is also directly proportional to the amplitude of the wave. So directly proportional means as one goes up, the other goes up. So if intensity and amplitude are directly proportional, then more amplitude means more intensity. So far, some of this should be familiar to you. Now, intensity doesn't directly tell you how loud something's going to be. Loudness is our perception of it. So we can measure intensity in decibels, and people talk about sound in decibels all the time. And you guys already know that something with more decibels is going to be louder, right? That's because loudness is how we perceive the intensity. And this can vary from person to person. You know how, like, you won't necessarily think something is really loud, but your parents might. It depends on the person, and it changes with age. So some people's ears can become more sensitive or less sensitive. So if you're sitting there and listening to loud music all the time, eventually it'll be harder for you to perceive intensity. So it'll be less loud to you. So loudness is subjective. It depends on the person, age of the person, and it's affected by something else. It's affected by the pitch of the sound too. And we'll get to pitch in a second. So loudness is how you perceive it. Intensity just is the amount of energy. So loudness is subjective, it's perception. It depends. Intensity is objective, it's measurable. Frequency is another aspect of a sound wave. And frequency is a measurement of the number of oscillations happening every second. So in your earlier wave stuff, you probably saw how waves are oscillations. There's something happening over and over. They're either an oscillation like this, or they go up and down. And this is measured in hertz, often shorthand to Hz. So you've probably seen this before too. Maybe in your radio, you may have noticed that you tune to, let's say, 97.5, and then you see the little symbols like MHz afterwards. That's the frequency of the radio station. And sound waves have a frequency associated with them. All waves have a frequency, and that can be measured. So frequency is objective. It's a measurement, a number. You can measure a wave's frequency, boom, you can calculate it. But the way we perceive frequency is called pitch. So you know what high-pitched and low-pitched sounds are like, right? High-pitched sound, low-pitched sound, ooh, things like that. And so the pitch, let's say the higher pitch sound, going back to loudness, remember how I mentioned it's subjective and affected by pitch? Well, if it's a high pitched sound, chances are you're going to perceive it as louder. Like if a little kid is just shrieking, then it's going to be a high-pitched sound, and you're probably going to think it's really loud and hate it. But a low-pitched sound, chances are, won't bother you as much. It won't come off as loud as a higher-pitched sound, and that's just all perception. And that was all there was that we felt was really important as far as the properties of sound waves go. So I'm going to go ahead and move on to electromagnetic waves now. Remember, I'm basing this off of what EdGenuity had there. There's a lot more we could say about sound waves, but I'm just basing it off of what was there. So moving on to EM waves, electromagnetic waves. Electromagnetic waves, their name comes from the fact that they have both electric and magnetic fields. So they just smash those things together and called electromagnetic waves. I'm going to be saying EM waves from now on. What makes them special, one of the things, is that they don't require a medium to propagate. And that means that they don't need anything to carry their energy. They can move through empty space, which makes a lot of sense. We get sunlight through empty space. It would suck if they needed something to travel through, because then we would never get any light from the sun. So they don't require a medium. Now, they don't need a medium, but they can be influenced by a medium. In fact, if they go from, let's say, outer space, which we're going to say is empty, to water, they're going to change their speed, because now there's stuff in their way, right? So their speed is going to be influenced by the medium they're in. The denser the medium, the slower they're going to go. So light, which is the best example of an EM wave, let's just say visible light, it goes fastest in empty space, which we'll call a vacuum. So vacuum, we're just going to say, means empty. So a vacuum has no particles in it, and they can go fastest through that. Water has stuff, and it's denser than air. So as soon as it hits water, it's going to go slower than it was in air or in a vacuum. So this right here is very important. Denser medium, slower EM wave. Now, in a vacuum like outer space, all EM waves travel at the speed of light. And that speed of light is a constant value. It is 3 × 10⁸ meters per second. This is the universal speed limit. This is as fast as anything can ever go. And this is how fast EM waves go in a vacuum. And we have a formula that shows the relationship between 3 different things: the speed of a wave, frequency, and wavelength. It's a very simple formula, and it's right here on the right. V is velocity, the speed of the wave. F is, of course, frequency. And this upside down Y is the Greek letter lambda, and it stands for wavelength. So this formula is going to stay on the slides for stay up here on the slides a few more times. Now, the speed of a wave depends only on the medium. So it depends on what the wave is in. If we have an EM wave and it's in outer space, it's going to go the speed of light the entire time. It's going to go 3 × 10⁸ meters per second, no matter what. Doesn't matter about its energy, doesn't matter about its frequency, wavelength. It just matters that it's in a vacuum. But if it goes into a different medium, then that changes, and we'll talk more about that in a second. So let's say we're talking about light going through space. Its speed is not going to change. So if the frequency of that wave increased, so if it has more energy, then it's going to have more frequency. But I just told you that the speed right here is not going to change. So if velocity is going to stay the same, and I increased my frequency, what has to happen to make sure that my speed doesn't change? Well, the only way to balance this equation still is going to be to decrease the wavelength. And that's what happens. When frequency goes up, wavelength goes down. And vice versa. If wavelength goes up, frequency goes down, if the medium stays the same. So down here at the bottom left, frequency and wavelength are inversely related. As one goes up, the other goes down. And this happens because the speed only changes if the medium changes. So if they don't say anything about the medium changing, don't change the speed. So frequency and wavelength, inversely related. Now, what if the medium changes? If it goes into a medium with a different density, the speed will change. And if speed changes, then the wavelength changes with it. Frequency doesn't change when the medium changes. That's because frequency is related to energy, and the energy of a wave doesn't change just because the medium changed. So if speed is changing, then that's going to change wavelength. So if the medium changes, then the speed will change. And the speed is going to change, so the wavelength is going to change. Frequency does not change when the medium changes. Now, these EM waves are organized based on their wavelengths and their frequencies. So EM waves have a wide range of frequencies and wavelengths, and we organize them into a spectrum, and we call it the electromagnetic spectrum. So down here is a basic example of how the EM spectrum is organized. The one shown below is going from long wavelengths. So you see how they're really spread out? Goes from long wavelengths to short wavelengths. So this is a basic EM spectrum. Remember that wavelength and frequency are inversely related. So over here, you have a very long wavelength. If you have a long wavelength, you should be expecting a low frequency. So you have really spread out waves that don't happen very often. Long wavelength, high frequency. Or sorry, low frequency. So the longer the wavelength, the lower the frequency. They are inversely related. And as you move along the spectrum, let's go over here and look at gamma rays. They are very short wavelengths. They're really squished together, and they happen a lot. So you see how we have a whole bunch of waves over here with really short wavelengths? High frequency, low wavelength. Also, another thing to remember, looking at the spectrum. So I mentioned earlier that frequency is related to energy. So the higher the frequency, the higher the energy. That's what it says here. Frequency is proportional to energy. So over here we have a low frequency. You should be expecting a low amount of energy. Radio waves are safe for humans. They don't hurt us. If you could see radio waves, you'd see you're surrounded by them. Our phones use them. Communications devices use them regularly. Radio waves are being beamed from radio towers to the radio in your car to then produce sound. So radio waves are all over the place. They don't hurt us. They're low energy. Gamma rays, on the other hand, have a very high frequency and therefore high energy. A gamma ray can kill living tissue quite easily. So sometimes they're actually used in cancer treatments. So when people say they're going to get radiation for cancer, they're talking about like in the gamma area. It can kill living tissue. So these are very high energy. High frequency, high energy. Low frequency, low energy. And the last lesson was reflection and refraction. So both of these are behaviors that light waves can do. So they make sense to talk about coming after EM waves, which are light. So when a light wave hits a boundary, it's gonna bounce off. This makes sense to us. And this behavior is called reflection. So this is probably the most familiar light behavior to you guys. You guys see reflection all the time. You guys see reflections all the time. And the direction that it bounces off at can be predicted using something called the law of reflection. The law of reflection says that the angle a light ray hits the surface at. So notice this picture down here at the right. So the incident ray is the original light ray. So it's the light ray right before it hits something. So here it is hitting this surface on the bottom. Well, where it hits the surface at, it's going to bounce off. And then now we have the reflected ray. Well, the angle that it hits the surface at is called the angle of incidence. And it's going to be equal to the angle it bounces off at, which is going to be called the angle of reflection. Where we measure this angle, though, is very important. So to measure this angle, we draw an imaginary line called the normal. and it's perpendicular to the surface the light is hitting. So the surface is down here at the bottom. So you would draw a line perpendicular to that. Remember, perpendicular means a 90-degree angle. So we have this imaginary line called the normal. And the angles we're talking about are from the ray to the normal. So the angle of incidence is from the incident ray to the normal. And the angle of reflection is from the reflected ray to the normal. And these angles are always going to be equal to each other. So if I have a 30-degree angle of incidence, I have a 30-degree angle of reflection, always. So this is important. Refraction is different. So reflection is what happens when a light ray hits something and bounces off. Refraction is what happens when a light ray hits something and goes into it. So if a light ray enters a new medium with a different density, it's going to bend. I mentioned to you earlier that when light goes into a new medium, it changes speed. Well, when it changes speed, it's also going to change directions. And that changing directions is the bending, that's refraction. So looking at this picture, originally the light ray was traveling at this angle. Then it entered a new medium. And when that happened, it changed speeds. And when it changed speeds, it bent. So you can see these are not pointing the same direction anymore. Now the amount that it's going to bend and the direction depends on whatever it's entering. Different mediums are going to bend light different amounts. That's why like when you put a pencil in water, you see the pencil is bent inside of the water. If you were to put the pencil in different materials, it could look more bent or less bent. Like for example, air is a medium. I can hold a pencil in front of me and it doesn't look bent at all, even though it is in a medium. But if you put it in water, suddenly it looks bent because now it's traveling into a different medium that has a different density. Now there is something called the index of refraction, and that tells us how much light is going to bend in a material. Each medium has its own index of refraction. So glass has an index of refraction, water has one, air has one. Every material has an index of refraction. You don't have to memorize them, just know what an index of refraction is. It gives you an idea of how much light is going to bend in that material. So media is the plural of medium. Media that have a higher index of refraction is going to bend the light more than a medium with a lower one. So looking at this table here, diamond is going to bend light more than water. So since it has a higher index of refraction, you would expect it to bend light more than water. And that's what that's telling you. That's all we would expect from you to do. I'm not going to ask you to calculate the index of refraction. Now, things you do need to be able to tell me. I should be able to show you a diagram like this, where you see that we have a light ray in a medium, and it bends. If it is bending towards the normal, that should tell you that it's entering a more dense medium. When light slows down, it is going to bend towards the normal. I will ask you a question like this. So this diagram is very important to you. When light enters a medium that is more dense, it is going to slow down and bend towards the normal. So make sure you can identify that. And the opposite situation is true as well. If light enters a medium that is less dense, it's going to speed up. And if it speeds up, it's going to start moving away from where it was pointing before. So if it enters a medium that is less dense, it's going to bend away from the normal. If it enters a medium that is more dense, it's going to bend towards the normal. So make sure you know those. Those are definitely going to be things I will ask you about. So that ends all the highlights from your EdGenuity lessons that you have for this week. If you have questions, please put them in Google Classroom, email them to me. You can put them in the comments of the video, but you'll get an answer quicker if you email me or put them in Google Classroom. Be sure to like and subscribe. I'll be posting at least a video a week for this stuff now. Also, if you have any questions, I can make a Q&A video. I will be having office hours on Thursday, though. And remember, your quiz is going to be posted Wednesday, and you'll want to try to get that done by Friday, so you'll be ready to move on to next week's content after that. And I will see you guys later.